Hi, my name is Vanessa Guzman, and today we're going to learn how to convert complex numbers into their polar and rectangular forms. So let's quickly review what complex numbers are. Complex numbers are simply the combination of both imaginary numbers and real numbers. Just because the name is complex doesn't mean these numbers are difficult to understand. They are more like a building complex, a building where two different buildings are joined together. In their form, a plus bi, a represents a real number and b represents an imaginary number. These numbers can also be shown visually. In the graph in the top right corner, we're going to be graphing the example 2 plus 3i. Our x-axis is going to become the real axis, and the y-axis is going to become our imaginary axis. So our real number is 2, meaning that it would be located here. And our imaginary number is 3i, meaning it's going to be located right here. Thus, the complex number will be here. The graph shown from the last slide is a rectangular graph. As mentioned, all complex numbers can be shown visually, and a common way to do so is with a two-axis graph. All complex numbers are converted into coordinate pairs, so their a plus bi form is a rectangular form. This is because we could dissect a and b and put them together as an ordered pair. This is because we replaced our x and y axes with the real and imaginary axes. Thus, x equals a and y equals bi. Now for the polar coordinates and form, we have to know that complex numbers can also be shown through polar coordinates. We can convert a plus bi into the equation z equals r cosine theta plus I sine theta. That is our polar form. Cosine theta and I sine theta play a crucial part in a complex number polar form. Let's look at our diagram to see why we derive these values. A is equal to 2 and b is equal to 3. R is obviously just a hypotenuse where we find through the Pythagorean theorem. We could find it by 2 squared plus 3 squared is equal to r squared, making it square root of 13 is equal to r. Continuing, we are sometimes given theta, but in this case we are not. Let's apply our knowledge of trigonometry to first find theta. We know that theta is located right here. Useful functions that incorporate our a and b values with theta are trig functions. We could rewrite a to be r cosine theta and y to be r sine theta. So since we know r is the square root of 13, we could find theta through x, known as 2, is equal to the square root of 13 times cosine theta by isolating the angle. We could do the same for our y/sine value. Now what if we haven't found r first? We could use both a and b through tan theta. Now to find tan theta from our tan function, we will be using arctan. Tan is simply equal to y over x, but in our case, it's going to be equal to b over a. So to find theta itself, we'll be using arctan of our b value, which is 3, over our a value, which is 2, giving us theta equals 0.92 radians. Now with these variables, we could plug it into our polar form and get the equation z equals radical 13 parentheses cosine 0.92 plus I sine 0.92. Now continuing on to our first problem, we are given the rectangular form and we need to convert it to a polar form. Let's quickly graph it, and that be here with our r value, that be -3, with our I numbers, that be right here at 4. So there is our points. We're going to be creating a little triangle for reference. With b and a, we know that b is equal to 4 and that a is equal to -3. So let's quickly find theta. We know that theta can be used by tan. So if we find tan value, which we know is b over a, in our case, it's going to be 4 over -3. And let's use arctan. So theta is equal to arctan of -4 over 3, giving us theta is equal to -0.927 radians. Now notice that this is negative. This is negative because it's from the ray that continues the line here. So it's this angle. But we don't want that angle. We want r theta, the theta we're looking for. So we have to add the additional step by adding pi to find r theta, which gives us 2.21 radians. Now let's quickly find r with the Pythagorean theorem. The Pythagorean theorem is simply a squared plus b squared equals c squared. In our case, it's 4 squared plus 3 squared, negative 3 squared, equals r squared, meaning that it's 25 equals r squared, or simply 5 equals r. Now it's connected to the polar form equation, which is z r cosine theta plus sine I sine theta, which is going to give us z equals 5 cosine 2.21 plus I sine 2.21. And this is our polar form. Now going on to our second problem, we are given the polar form and we want to convert it to our rectangular form. Now we know from a polar form equation that radical 41 is our r, and these two numbers are our theta. Now, since we're only given r and theta, we should know from our past examples that x is equal to r cosine theta and y is equal to r sine theta. Of course, x represents a and y represents b. So if we could just plug in these numbers into these two equations, we could get a and b. From a and b, we will then connect it to our rectangular form equation, which is z equals a plus bi. So let's quickly plug these in. The square root of 41 cosine times 2.47 is x, and the square root of 41 sine of 2.47 is y. If we plug these into the calculator, we're going to get x is equal to negative 5 and y is equal to 4i. Now let's quickly plug it into our equation. We're going to get z equals negative 5 plus 4i. Now let's quickly plot these for reference. Negative 5 on our real axis is located right here, and 4 is located here, which means our point is right here.